Behind me is a very interesting and pretty challenging combinatorial problem. We want to find the number of subsets of this entire set that have the sum of its elements to be divisible by 4. Now, as I said, this problem is pretty interesting. However, the reason for that is we can actually use complex numbers to solve it. I'm being 100% serious. If that surprised you even by a little, then I highly encourage you to right now pause the video and try this problem for yourself. Done? Did you at least try the problem? Okay, so how can we deal with a problem like this? We might start by considering casework on the number of elements in the subset. So maybe we can consider the case when there are 0 elements, 1 element, 2 elements, and so on. But that can be pretty challenging because we have 1001 cases to consider in that case. Every single length from 0 to 1000 is possible. So, not going to be easy. Okay, so if that's not going to work, then what can we do? Well, I'm thinking about, is there a way I can algebraically model the sum of the elements in any subset? And you might be wondering, what do you mean by algebraic model? This is a combinatorial problem. What do you mean by algebra? Well, what I mean by that is, can we find a generating function for the sum of the elements in any subset? And you might be even more confused, like, what is a generating function, right? Okay. I think the best way for me to explain what I mean by generating function is by considering a simpler example. Okay, so I've simplified our set. Here we only have the numbers from 1 to 5, whereas here we had 1 to 1000. Now, we can use a function to model the sum of the elements of any subset of this set. And this function is f of x is equal to 1 plus x times 1 plus x squared times 1 plus x cubed times 1 plus x to the 4 times 1 plus x to the 5. And I know this looks pretty confusing. I mean, what does this polynomial have to do with this set, right? And furthermore, what does x even represent? I just introduced a new variable without any definition. What does x mean? Okay, those are indeed valid questions. However, my answer to the latter question is just think of x as some sort of placeholder variable. What's more important here is actually the exponent on x. And here I might note that the exponent is 1, right? So these exponents are actually very, very important. And also, I want you to treat this 1 over here as x to the 0. Now, pay attention to each of these binomials that we're multiplying together. Each of these binomials represent a binary choice. And let's just take this as an example. This represents a binary choice of whether you want to include 1 in the subset or not include 1 in the subset. And the 0 makes sense because if you don't include 1 in the subset, then the numerical value it's adding to the sum is 0. But if you're including 1 in the subset, then the numerical value adding to the sum is just 1. And it's the same for each of these binomials. You can include 2 or not include 2, include 3 or not include 3, and so on and so forth. Now, let's just make a combination of choices, okay? Let's just say that we choose to include 1 in the subset, we choose not to include 2 in the subset, we choose to include 3, we choose to include 4, we choose not to include 5. Now, because we're multiplying the binomials, let's just see what happens if we were to multiply these terms. We have x to the 1 times x to the 0 times x to the 3 times x to the 4 times x to the 0. And if you were to multiply this out, you would get x to the 1 plus 3 plus 4. And the reason I have written it as a sum up here is to show you how, notice that when you make a combination of choices, when you multiply those terms together, the exponent will be modeling a possible sum you can get. In this case, if you choose a subset with elements 1, 3, and 4, then this over here is telling you that the sum of the elements is 1 plus 3 plus 4. So this exponent models the sum, and this is x to the 8. So 8 is a possible sum we can get. And here's the even cooler part. If you were to take this entire polynomial, this factored form, and you FOIL it all out, you multiply this entire polynomial out, you write it in standard form, then, let's just take this x to the 8 as an example, then, before simplifying, you're probably going to have multiple x to the 8 terms lying around in the expanded version, right? Now, what do we do when we see like terms? We usually collect them. So we're going to have a coefficient in front of x to the 8. Now, what does this coefficient represent? Well, remember, each of these x to the 8 terms came from a way of having the exponent add to 8, which is corresponding to a way or corresponding to a subset that has a sum of 8. Therefore, this coefficient tells you how many subsets there are to get a sum of 8. And this is the same story for literally every single other number. If you have the coefficient of x to the n, say an, then this an tells you how many ways there are to get a sum of n. And that's the meaning of this generating function. Okay, now that I've explained the generating function, we can similarly say that this function f of x equals to this will model the sum of the elements of any subset of this set. Now, as I just said, the coefficients in standard form are the most valuable to us. However, this is in factored form, and there are 1,000 factors. There's no way I'm going to be expanding all of this and collecting the like terms just so that I can see it in standard form. However, we know that there will be a standard form, whatever that is. So let's just call it this. Let's just say that the standard form is a0, our constant, plus a1x plus a2x squared plus a3x to the 3 plus a4x to the 4 plus so on and so forth, all the way to an x to the n, where n is the highest degree, okay? Now, note that a0 is just 1, because you just have 1 times 1 times 1 times 1. That's our constant term, so it's just 1, right? However, I'm still writing a0 to give generality to this polynomial. Now, notice this. We don't know the coefficients. Yes, that's true. We do not know the coefficients exactly. However, notice that this problem doesn't require us to get any specific coefficient. In fact, it's just asking for the number of subsets where the sum is divisible by 4. So this a0 over here counts because the sum is 0, right? And 0 is divisible by 4. So this a0 counts towards our total count. But our subset can also have a sum of 4, and the number of subsets is a4. So we can also have a4 added to our count. And so is the same story with a8 and a12 and a16 and so on and so forth, right? Any coefficient where the index is a multiple of 4 can be added to our sum. So actually, we just want to compute this sum. We don't need to find each individual value. We just want to compute what this sum is. But this doesn't really look that easy to compute. I mean, the indices are skipping every 4 values. How do we filter that out? How do we filter it from this polynomial? Okay, before we try to evaluate something as complicated as this, we might want to just first start by playing around with this function. Just get a foothold and see what this function can give us. So let's treat this function as something we can actually evaluate at certain values of x. Well, one certain value that I want to try is x is equal to 1. Let's try evaluating f of 1. Well, notice that if we just plug in x to be 1 for each of these x's over here, then we just have 2 multiplied with each other, and it's multiplied 1,000 times. So f of 1 is just 2 to the 1,000. But now let's plug it into the standard form polynomial. Plugging x is equal to 1 gives us a0 plus a1 plus a2 plus all the way until an, right? And notice what this means. This means that we have a sum of the coefficients, and the sum of the coefficients will tell us how many total subsets there are, right? And it's equal to 2 to the 1,000. So there are 2 to the 1,000 different subsets we can form. Now, this isn't actually very impressive because we could have gotten this at the start. If we want to construct a subset from this set, then each of these elements have two options, to be in the subset or not be in the subset. And there are 1,000 elements each. There are 2 to the 1,000 subsets. So not very useful, but it's still pretty cool that this function can give us some true information. Okay, well, what other values can we play around with? You could try f of 0, but you'll see that isn't really impressive. It's not really a cool thing to evaluate at when you actually try it. However, I'm thinking of x is equal to -1. What happens if we try evaluating f of -1? Well, firstly, just plugging in x is equal to -1 here will get you 1 minus 1, and that's 0, and then you just have a product. Well, the product goes to 0, so this is just 0, right? Furthermore, if we were to plug it into this standard form polynomial, then we get a0 minus a1 plus a2 minus a3 plus, you get the point, it's an alternating sum, right? Plus all the way until -1 to the n times an. Now, is this actually useful? Maybe not in the context of this problem, but this is actually some new information. Because notice that if the index is even, then it's going to be a positive, right? If it's odd, then it's going to be negative, right? And notice that this alternating sum, the sum of the even coefficients plus, sorry, not plus, the sum of the even coefficients minus the sum of the odd coefficients, this turns out to be 0. And this is telling us that there are an equal number of subsets which give you an even sum as the subsets which give you an odd sum. Pretty cool, right? Now, here is the most fundamental part, and this part will actually be a foothold for solving this problem. Notice what happens if I were to add these two equations. On one side, adding gives you 2 to the 1,000, right? And on the other side, notice that here we have 2a0, and then here this is plus and minus, so this just goes away. And we have a2 plus a2, that's 2a2. And, well, you can imagine that the a3 will cancel out, right? So actually, notice if you were to add the equations, on this side, you just get 2 times the sum of the even coefficients. And if you were to divide both sides by 2, then you just get that a0, I'm running out of space, but it's a0 plus a2 plus a4 plus so on and so forth. The sum of the even coefficients will be 2 to the 999. So there are 2 to the 100, sorry, what? I don't know why I started boxing this, but there are 2 to the 999 subsets, which will give you an even sum. This looks very close to what we want over here. Here, the coefficients were skipping every 2, right? But over here, the coefficients, or the index rather, was skipping every 4. How can we convert a problem where we skip every 2 to where we skip every 4? Let's try to consider what we even did to create this filter in the first place. Notice that this number of -1 had some very special properties in this case. When you were to multiply it successively to 1, you would get a cycle of length 2. And what I mean by that is, if you were to take 1 and you multiply it by -1, you would get -1, right? And you multiply this by -1, you just get back to 1. So multiplying this by -1 periodically will create a cycle of length 2, right? You get 1, -1, 1, -1. It oscillates. And this oscillation is what helped us basically create the alternating signs, right? Here we had plus and then minus for the odd coefficients because of this cycle of 2, which was what enabled us to add the equations and cancel out the odd coefficients. However, instead of creating a cycle of length 2, can we create a cycle of length 4 for this sum? Well, for a cycle of length 2, we found the number -1. But cycle of length 4, that's a bit weird to think about, right? There might not be a real number that will allow us to create a cycle of length 4, but there is a complex number that will allow us to do that. Consider this. If you were to start with the number 1 and you multiply it by I, then you would get I, right? If you were to multiply this by I, then you just get negative 1. And if you multiply this by I, you get negative I, right? Sorry, let me just write that again. And if you multiply negative I by I, that's just 1. So notice that when you were to start with 1 and you multiply each successive number by I, then you create a cycle of length 4. It oscillates in a period of 4 in this case. And this is extremely useful. Now, I want to make a quick note about generalization before we move on. If you were to take I, right, I over here, and you write it as exponential form, which is e to the I times 2 pi over 4, and I've intentionally not simplified this fraction to help you see what's going on here. Notice that this form, this argument on the top, is saying that I divides the entire 2 pi angle into 4 pieces. And this is what exactly makes it possible to start at 1 and successively multiply by I to create this cycle of length 4, because it divides the 2 pi angle into 4 pieces. And similarly, if you were to start at 1 and multiply successively by e to the I times 2 pi over n, then you can actually create a cycle of length n. And this is a very good generalization because we can actually replace this 4 with n and solve the problem altogether. This is actually a very good generalization. I'll go more into this at the end of the video, but as of right now, let's continue solving our problem with I. Okay, give me a second. Okay, so notice that, again, we were able to create a cycle of length 4. And each of these 4 numbers over here in the cycle, if you were to take them to the 4th power, they would always be 1. So therefore, if you were to take any 4 of these values and plug it into f of x, and if you were to consider the standard form of the polynomial, and if you were to consider each individual term, then notice that every single term with degree, which is a multiple of 4, if you were to plug in x for any 4 of these values, they would just get you the coefficient. And this is what makes them so good for filtering out every coefficient with the multiple of 4. So this is one key fact. Another key fact is that if you were to take a term whose degree is not a multiple of 4, so let's just take x to the 3 as an example. So that's a3 x to the 3. If you were to evaluate f at each of these 4 values and then add those equations up, then notice what happens to this x to the 3 term. We're just going to consider this one as an example. Well, at f of 1, this will become a3, right? And at f of I, this would be negative I times a3. And at negative 1, this would become negative a3. And if you were to plug in negative I for x, that would be plus a3 times I. And notice this. They cancel away. They cancel away. You add them up, they cancel away, right? And this is what makes them so good. You're able to filter out every single coefficient which is not a multiple of 4. Now think about why this must be true for every single coefficient which is not a multiple of 4, right? Why must the coefficients always cancel out? Think about it on your own. Okay, so now we are going to finally solve the problem. In the case where we had every even coefficient, we evaluated f of 1, so f of 1, and then plus f of negative 1. Negative 1. Right? We used the numbers in the cycle, and that's how we calculated a0 plus a2 plus a4 plus so on and so forth, right? Now, we want to calculate this sum, which involves a cycle of 4, so we're going to consider computing f of 1, so f of 1, plus f of I over here, right? And then plus f of negative 1, right? We're using the numbers in the cycle, f of negative I. And as I just said, if you were to add all of these values, then the terms with a degree which is not a multiple of 4 will always cancel out. We've seen that in the example with x to the 3. And furthermore, notice that whenever the degree is a multiple of 4, then it will always be 1, right? We'll just have a4 plus a4 plus a4 plus a4. There are 4 of these, right? So a4 times 4. And it's going to be the same for every single term with degree a multiple of 4. So over here we have 4 times a0, and then we have plus 4 times a4, and then 4 times a8, and then plus so on and so forth. It's just 4 times this desired sum. Now, what is this equal to? We don't know what the value is, right? What is this? Well, we can use this to evaluate this. Notice that by the factor form, we have f of 1, which is just 2 times 2 times 2 to the 1,000, right? So 2 to the 1,000. And then we have f of I. Now, notice this. F of I, just pay attention to this binomial over here. I squared is -1, and then 1 minus 1, that's just 0. So this product drops to 0 for f of I. And f of -1, well, over here, that's just 0. So this is also 0. And then f of -I, well, consider this. Plug in -I for this term again. This will be 1 minus 1. That's just 0. So that's just 0 again. So this is just 2 to the 1,000. And finally, for brevity, if we were to call this s, okay, then notice that here we have 4s. This is equal to 2 to the 1,000. And finally, we can get what s is. S is just equal to 2 to the 998. Therefore, this is the number of subsets where the sum of the elements is divisible by 4. Actually, this method of filtering out certain values with complex numbers, they are called the roots of unity filter. And this is because we're using the roots of unity to filter out the desired terms. And as I said earlier, we can create a generalization with this method. Instead of just using I, which is equal to e to the I 2 pi over 4, where we cut the 2 pi angle into 4 pieces, instead of this, we can generalize to e to the I 2 pi over n in order to create a cycle of length n. And this is super useful if we were to replace this 4 with n. If I were to instead ask you to compute the number of subsets with this property, except it's divisible by n, then this complex number is actually super helpful for generalizing this problem. So yeah, try it for yourself, and then maybe use the generalization to solve this problem, right? Or even this problem, right? All of these are super powerful methods for generalizing a problem like this. Okay, I hope all of this was very clear to you. I hope you see the power of generating functions and complex numbers. We used two things that seemed very, very unrelated to counting. One, a polynomial, and two, complex numbers. Never in my dreams would I have thought that these two things would ever be involved and would be so powerful in counting. Anyways, thank you very much for watching this video. If you found this video helpful, if you found it interesting, then please do consider dropping a like and subscribing. Thank you very much. Bye.